I had to dust this one off, actually. I think Sean suggested it, and I think it was a pretty good idea. Sean Wu and I and Wayne Ruth first gave this presentation at APT in Montreal in 2008. So it's been a while. This project we actually worked on in 2007 and 2008. And I think it's a really good little kind of a case study, but also an educational bit for all the engineers. I'm happy to have engineers here because I was worried about a couple slides in there, but we'll talk about some engineering things. And this project was good for us because it involved really all phases. We got involved in the condition survey, design of some masonry strengthening techniques and quality assurance, implementation, and all of that. The bad side of the project, we will see, we got involved way too late after all of the engineering and architectural design decisions had been made, and there were some, this is on tape so I have to be diplomatic, there could have been better decisions made. So we're going to talk about it, and for about, this isn't so long, it's about a half an hour, maybe a little less, and then I see Drew and Zach kind of working frantically out back. We have a little mock-up. We just built a little, like a 2-foot by 3-foot mock-up, and we'll do some injection. We'll do a little injection, we'll do a flow test, and I have some, some core samples from other older projects that you can see how the injection process works. And it's something we've been working with Masonry Solutions on since 1993. And we've worked on together, over 200 buildings across the country, a couple international projects, and a lot of really interesting things the last few years. But we're going to talk about this particular building, the Sociology Building at University of Missouri. It was built in 1892. Anybody know anything about University of Missouri? They have the world's oldest journalism school, opened in 1908, and unlike CU, who just closed their journalism school and then renamed it, something happened there, right? They were actually had a big donation from the Reynolds Foundation to expand and modernize their journalism school for the 100th anniversary in 2008. And part of that project was to take what was the Sociology Building, this building you see here, and renovate that for modern use and link that through some glass atria and walkways to adjacent journalism buildings. So that's the core of this project. And unfortunately, this is how the building looked when we first got involved. Actually during the construction phase, and we got involved. We've had a series of projects for University of Missouri over the years, and the campus architect, after they started gutting the building and ripping down interior bearing walls, decided that these 45-foot tall unreinforced brick walls were a little bit scary, and they called us in to take a look at things. And unfortunately, this was really the worst thing about this project. It was just way too late to begin making decisions about what to do with the historic brickwork. And it's a beautiful building, and as it existed originally, there were 2 floors above grade. There was a basement level. And the architectural scheme was actually tearing out all of the interior floors, taking out all the interior bearing walls, lovely, and where there were 3 stories before, they had a kind of a building within a building that had 4 floors. So they actually lowered the basement by 5 feet and took these really like 13-foot floor heights and changed them into like 11-foot or 10-foot floor heights and put in 4 floors. And I'm not a big fan of that approach, but unfortunately we weren't there early enough in the project design development to give the architect and the campus a hard time about it. But our role really was to help the construction team and the engineer figure out how to best stabilize these walls, not only during construction but for the finished project. And also how to resist some huge loads that were coming in at new roof beam bearing points. So I think you see, if you tear out interior bearing walls, that load's from the roof, it has to go somewhere. And it got concentrated at specific points, here and here, for instance. There were a series of points we'll see in a moment. I think actually in this slide here where there were some really huge bearing loads were concentrated. So here are the concerns. The wall really had a fairly poor initial construction quality, and this puzzled us for a long time, but the mason from Masonry Solutions came up with, I think, was the right answer. Here's a wall section. You see 2 Ys, 8 inches of brick, pretty well built, fairly solid. And we see a face brick Y, with thin mortar joints, thin buttered joints, and in between those two is kind of just whatever was thrown in, and a lot of voids, a lot of openings, and incompletely filled wall sections. And the mason said, well, sometimes that happens where they'll have one crew on the inside building the common brick, these inner 2 Ys. They'll have another crew on the outside laying up the face brick because it takes a bit more precision. And it probably the common brick guys got ahead of the face brick guys, and they just kind of filled in with rubble whatever they could at the interior. So there was some concern about that. That wasn't a huge issue. The big deal was some potential instability of the walls, height to thickness ratios of the walls, depending on how you looked at it. If it was just a 2-wide wall or a 4-wide wall, well connected, well bonded, it either passed or it didn't. These height thickness ratio requirements. We talked about point loads. That was a big issue. We'll see how we approach that. And yeah, as I discussed already, they added an extra floor in this building and actually lowered the basement by 5 feet. And yeah, that introduced a whole series of issues into the foundation and the stability of the stone foundation. So here's a plan view of the building, and I think you can see. I thought I had in blue, but here we go. These little black points here. The dotted lines are where the interior bearing walls were removed or planned to be removed as part of the construction. These little darkened areas are where the new roof supports were bearing, and there were some really big bearing loads coming in, 9 kips to 83 kips. Most of these, a typical bearing load at these points was about 32,000 pounds, and that's the problem. They didn't put a lot of thought into how the old brickwork was supposed to handle those big point loads. So that received a lot of attention. And here's one of the details from the original design showing what they're doing with the foundation. So they're actually lowering the floor at the interior of the building by 5 feet. The original foundation depth is here, underpinning the stone foundation. And again, it's a great detail, and structurally it checks out, but how do you get to that point, and how do you ensure that you have a stable stone, rubble stone foundation in between the bearing points? That was one of the main issues that was addressed. So we started with helping them out, helping the engineer out, and I'm trying to remember who actually hired us. I think we were hired by the University of Missouri, but we worked real closely with the engineering firm, well-known firm. We worked with the architect, and I'm not in the habit of throwing people under the bus, but they went into this project without really any information at all on how these walls were built, what type of compressive strengths to expect, and as luck would have it, this was really one of the most poorly built and very soft, with very poorly constructed with original materials, had low strength, low stiffness, very low strength that we found during some of the condition surveys. So we ran condition surveys. We looked at the as-built condition, visual. We did a visual condition survey, used radar. We'll see how some of that works. We looked at the current condition of the mortar joints, the interior conditions of the walls, and very importantly, the engineering properties of the brick masonry itself. We'll talk about each of these. Now, these were some holes cut in walls by others. These were there when we showed up on site, and they had a whole series of interior bearing walls that they were going to demolish. So, in effect, taking samples like this out of the wall and into the laboratory kind of made sense in this case. These walls were going to get torn down anyways. The problem is, due to the very poor bonding quality of the original mortar, the test lab really could not get intact specimens back to the lab. It just came out as rubble and just loose pieces. And what was even worse, their results were unreliable. I mean, they had test results ranging from 300 to 1200 psi compressive strength for the masonry. I have no idea how they got 1200. I think maybe they tested a brick alone and not an assemblage. But you know, the engineers really didn't have confidence that they could rely on the test lab's results. And so we did a series of flat jack tests, and Sean was involved in a lot of that. And you guys have seen a flat jack before, probably. We'll pass one around anyways, come on. I cleaned it up and everything. I got all the oil off it. That's a flat jack. It's a little hydraulic pressure cell that is placed in a mortar joint, and two of them, one above the other. When you pressurize it, you read surface strains, and that gives you a real nice, what engineers love to see, is stress strain curve. And you know, we ran a series of these tests. Here's 3 of the results from one wall type, and they were showing us a compressive stress in the range of 400 to 500 psi, say. Remember that number, 450 psi. That becomes really important in a minute as we look at some of the bearing stresses that, that were designed into the system. So, ran some flat jack tests. We also tested brick. It really wasn't necessary as part of the project, but remember, a component of the solution here was looking at injection of internal voids. And to design an appropriate injection material, we need to know basic characteristics of the brick, how strong it is, how absorptive it is, and that goes into designing of our compatible injection material. But that's important, but what kind of struck me was that these were hugely absorptive brick. They had a initial rate of absorption much greater than a typical limit, which is 30 grams per minute per 30 inch squared, that we see in a lot of modern specs. I think they're about 70 grams per minute initial rate of absorption, and that means that made our injection job a whole lot tougher in terms of dealing with how these brick absorb water out of any material that's injected into voids inside the wall. We look at compressive strength and all that. We ran a series of radar investigations to understand better the distribution of voids throughout the building. And I don't know if you've seen radar traces before, but here's 2 of them. As you run a radar antenna down the wall, it spits out this type of a trace. So along this axis, it's just length down the length of the wall, distance, and vertical axis is depth within the wall in inches. And let's start with this one, because this was a pretty solid wall over here, and we had a pretty good estimate. The walls measured about 17 inches thick. I think we had everything calibrated. We're sending this radar trace through 4 Ys of brick and getting a reasonable reflection from the back of the wall there, and not many reflections from the interior Ys, and that to me means a pretty solid wall. This other radar trace here on the left, you see our depth estimate is a little bit off. It's because we're passing through a whole series of air voids within the wall construction. So using radar scans, we didn't scan the whole building, but 10 representative areas, say, we got a pretty good idea of the distribution of voids in the collar joints and how those voids existed throughout the building. Borescope, there's a borescope image, and looking down inside the wall, you see brick and mortar and a void space, and that's pretty typical. Whenever we think there's voids inside walls, we like to open things up and look at it with a borescope, and that's just inserted through a little 1/2-inch diameter hole drilled into mortar joints. I'll tell you a really interesting thing on this project, and I think it's applicable to a lot of buildings we work on in the Denver area. I don't know, you walk up to an old building, if you don't see header courses, you start scratching your head, right? Okay, how do they tie it together? Are there metal ties? In this case, they use blind headers. We call them diagonal headers. I just ran across a reference that from the early 1900s. It's just called this running bond headers. Hidden headers within the wall, and these are diagonal headers were formed by the mason to have to kind of chip off the backside of 4 brick for every diagonal header, and they didn't like to do that because it took a lot of labor and a lot of time, and I see this a lot on homes in Denver where the diagonal header system was used. They're not always where they need to be, and in this case, using radar, we were really successful at locating exactly where these header courses were, and you can kind of see them sticking out of the backup wide. We found them to be typically 6 to 10 courses apart at the piers between windows, and that was great. I think that was adequate. But there were no headers at all on these spandrels, and that answered one really important observation, or the root of that observation was that we saw a lot of bulging and some funny deformations of the walls at the spandrels, and because they just weren't tied back properly. And I mentioned the Denver connection here because I don't know about you guys. It seems like we've fixed a whole bunch of buildings in Denver circa 1910, say, that use this blind header system because, number one, the building had moved a little bit, the headers don't grab on as well as normal headers, and the exterior wire that slipped. And number two, that the masons just didn't put them in where they were supposed to all the time. So because of this observation, we came up with some solutions. We'll see that in a moment. Now, we ran some pendulum hammer rebound hardness tests to look at the mortar hardness throughout the exterior and interior. The building had been repointed 15 years prior, and like a lot of repointing projects, there was concern that maybe they used too hard a mortar, a high cement mortar. So luckily though, with the results of this hardness test, testing the hardness of mortar at different areas around the building, we found that the repointing mortar was only maybe 25% harder than the original mortar. And that's pretty good. And we helped the university make the decision that they did not have to rake out all that old repointing or the new repointing mortar and repoint the whole building. And that saved them tens of thousands of dollars, and they were all happy. They weren't so happy about some of our other findings. That cost them hundreds of thousands of dollars in engineering upgrades, but that's the breaks. That's how it is sometimes. I think the last test I want to talk about, we call it the Lujan test method. It's Lujan testing, comes out of soil permeability testing. It's a method that we use to look at if a wall is suitable for injection. And this is actually Romeo, one of Masonry Solutions guys, was doing this Lujan testing at the stone foundation wall. And it's just introduction of water into say an injection port at low pressure. There's a digital flow meter, and depending on the flow rate into the wall and how well it comes out adjacent ports, I don't know if you notice water coming out here, that gives us an idea and actually a definitive measure of if this wall has a large network of interconnected voids or if it's a very fine network, and it helps us to choose and design the injection material. In this case, 80% of the holes had a very high flow rate, meaning the foundation there are a lot of voids pretty wide open on the inside, and that pointed us in one direction. Good for engineers. We like talking about codes. You guys know about all these, right? You know, using modern codes for looking at historic buildings is problematic because modern codes were designed for modern materials, type S mortar, type N, concrete block, hard-fired brick. You get yourself in trouble pretty quick if you use the modern code for historic materials. So we tend to use, you know, a combination of approaches. We don't have nationally any single code that tells us as engineers how to deal with historic construction. So we use Chapter 5 of the MSJC code, some of the empirical design requirements, and two seismic-based codes. And University of Missouri, they were outside of the main seismic zones. It wasn't a seismic rehabilitation, but we still use a lot of the concepts. I mean, shear strength to shear strength, compressive strength to compressive strength. The analysis methods still are valid. It's just on the load side, we don't use the seismic side of these codes. And so we followed some of the requirements in specifically ASCE 41. So here's our initial issue. We've seen this image before of the cross-section of the wall. And you know, the best way I can explain this wall, this 18-inch thick wall, was really as an 8-inch wall with two 4-inch walls kind of just happening to be standing there next to it. And the main concern was in how those four Ys of masonry were working together. And because of the many internal voids and this rather poor connection with the blind headers, sometimes there, sometimes not, maybe not grabbing on as well as we need to, and really made worse by the decision to have these walls spanning really 40 feet between connection points. Remember, they're taking out all the interior floors, all the interior bearing walls. They can't do that, without having monolithic action between all four Ys. So we came up with a recommendation to pin the face brick to the backup where the blind headers were missing, and then injection to fill these internal voids. And guys use Helifix ties? You've seen them? Here's the Helifix tie if you want to pass it around. It's, I think, about the best approach going, and certainly the most cost-effective approach for pinning Ys. It's not great as a structural anchor. You don't get much more than 300 or 400 pounds out of each one. But you see, they actually did this work from the exterior. You see the little holes at the intersection of the bed and head joints. So a whole lot of Helifix ties went into the exterior. We worked with Masonry Solutions. We've been developing their mixes since 1993. And we first got involved with injection on a project for the National Science Foundation in '91, looking at how do you fix earthquake damage in buildings. Crack repair, crushed masonry, displaced masonry. We looked at a whole series of techniques, and it was a neat project with CU and University of Milan and a Slovenian group, and came up with really one of the best methods to address seismic damage was injection of grout material. And we've since that time gotten really good at formulating different mixes. And the key to developing these mixes is that it has to be compatible with the existing masonry. It's actually really easy to come up with a material that's super strong and flowable and get into tiny cracks and fissures. The challenge is coming up with a low strength, high compressibility, low elastic modulus material that is compatible with historic brick. And vapor permeability also comes into play. And just like we do with mortars, we tend to stay away from high cement injection materials. We go with a lot of high lime materials, add mixtures, and we'll see how that works in our little demonstration in a few minutes. So we built a mock-up panel using brick from on site. This actually looks a lot like our little mock-up that we're going to see a little later. And you inject it and do compression specimens and take cores out of it and look at the shear bonds, how well the material bonds to the face brick. And all that comes into play with designing the injection material. So that's the first step. I think the big issue really from an engineering standpoint was all these huge point loads coming in at these I think there were eight or 10 locations. And these are areas where there were new beams and new trusses supporting the roof that was previously resting on these bearing walls, right? These bearing walls being removed, and all those loads getting dumped into these discrete points. The original architectural plan was to infill and to cut channels in the walls through 13 inches of brick, leaving the face brick there, and backfilling that with reinforced concrete members. And it sounds okay, but there's such a huge stiffness mismatch between modern concrete and historic brick. I'm convinced, it would have cracked up like mad. And the face brick would have had cracks, the adjacent brick would have cracked up, and they gave us a hard time about that because our plan did not include reinforced concrete. I'm not so sure it was any more expensive than concrete, but they gave us a hard time about deviating from that concrete plan. But I felt vindicated because about a year, maybe 6 months, not a year, but 6 months after we were done with our work, they had infilled some door openings with concrete block, actually beneath some beam bearing points. Like up here was a main bearing point. I said, you can't do that, it's too stiff, it's gonna shrink, you're gonna get cracks between the old, I wanted them to use some of the reclaimed brick and fill in that panel. And the contractor actually called and said, you know what, you guys are right. We got all these cracks everywhere where we infilled with concrete block. And I'm really glad that they didn't follow this approach everywhere because, this historic brick wall system would have been crisscrossed with a whole network of reinforced concrete members, and I think the viability of that was very suspect. So We talked about a bunch of different options. You know, this reinforced concrete infill, we just decided that wasn't viable. We could have saved all the work I'm going to talk about by leaving just little bits, like 6 feet of these interior bearing walls, but the architect wouldn't do it. He wouldn't do it, and that meant really hundreds of thousands of dollars of intervention to strengthen the masonry that was there. So I think the best solution that everybody got together and decided on would work was using the existing brick, spreading the loads out, getting solid walls beneath these bearing points, and installing confinement reinforcement within the wall. And that's pretty interesting. So the first step really was designing a reinforced concrete bearing pad, if you want to call it that, underneath the beam bearing points. And you know, originally, these walls were designed by the engineer to be under about 200 psi stress. Sounds pretty low, but remember I told you, what was the compressive strength? Somewhere between 400 and 500 psi. 200 psi is way too high. They would have seen cracks. They would have seen long-term creep issues. They would have seen big problems. Maybe not immediately, but 5, 10, 20 years down the road. So we looked at 2 different criteria. The existing building code says, you know, 100 psi max for old brick. The MSJC gives us, you know, 25% of F prime M. That got us in 112 psi range. So we were designing for 100 psi max. I think there was one area went up to 105 psi, and I feel pretty comfortable with 100 psi in old brickwork. I think it can handle that. So the second concept is really looking at how loads spread out from those bearing points. And with modern masonry, we know how to do it. We have design approaches. I couldn't find anything that told us how to do this for old, soft masonry, and it comes into play because we had to size these concrete bearing pads up at the tops of the walls. So how does this load spread out, and maybe most importantly, how wide does that load spread out to? And we used a classic Timoshenko approach, looking at this concrete beam resting on a somewhat flexible foundation, which is the masonry wall, and found that loads tend to spread out to a maximum, you know, effective width of about 4 times the wall thickness. That was pretty interesting because I know if we're designing modern masonry, I usually assume load spread out to 6 times the wall thickness. It's kind of a rule of thumb that's written into building codes and all. And so 4 times the wall thickness made sense to me just because old masonry is not as stiff as modern masonry. So we've got those beam bearing pads designed. We've got them sized, we've got the length, the width and all. The next step was to actually look at what type of confinement reinforcement to get inside these wall sections. So we know as we compress materials, right, as they get shorter, they also tend to spread laterally. That's the Poisson effect. And for reinforced concrete columns, we normally put confinement reinforcement or hoops in the column. That's, you know, hoop steel, the reinforcing bars to counter that spreading effect. And we actually designed confinement reinforcement to go internal to the walls. And really just to take this lateral spreading effect into account. So here's a concrete bearing pad. Our point load was coming in somewhere up here from one of the main roof trusses. And we ran our confinement reinforcement a distance of 8 feet from the end of the wall. I think if you followed our analysis, it spread out more like 6 feet. We just ran the confinement steel beyond the spreading point a couple extra feet just to make us feel better. Stainless steel reinforcement, here's a plan view. A series of horizontal and bars really to take and to handle the tension stresses that develop due to that lateral spreading, that Poisson effect. So at the inside face of the wall, it was installed by just raking out the joint and putting a piece of steel back deep in the wall. At the exterior face, they wouldn't let us do that. We couldn't touch the exterior face brick for any of this work. So at jams, at door and window jams, they would drill in horizontally 8 feet and insert the bars that way. And we had some overlap, to develop the the strength of those bars, some hooked bars around the corners, and you'll see that in a moment. And it worked really well at piers between windows because, you know, they could physically drill in and hook the bars around the jambs. It worked well at ends of walls. Didn't work so well at spandrels. And so we came up with a different approach. All these little dots here represent diagonal stitching reinforcement. And this was a methodology that was developed by a fellow, Dr. Lizzi, in Italy back in the 1950s. And they've used this approach on dozens of buildings in Europe and Asia. One building in the U.S., and this was the second building in the U.S. And essentially, it's a diagonal cross-stitching pattern that does the same thing as our normal circular or semi-rectangular hoops. Again, the intent was to increase the bearing capacity and take the tensile stresses that develop in walls as a result of those high compressive stresses. So all this work was done from the interior. They actually drilled to within 2 inches of the exterior, and so in plan view, these little, actually they brought a little piece of one, these stainless steel bars were inserted, and the holes drilled at a 30-degree angle each way, and they're also drilled at a 30-degree angle up and down. Got a little complex. And this is how some of the reinforcement looked on the inside. You know, beneath these here's a main beam bearing point. This wall was actually getting demolished. They let us keep this part. That's it. And so looking at the, you can see the confinement reinforcement installed in the mortar joints and across the wall there. And it was pretty complex technically, and the Masonry Solutions guys did a great job. There were something like 5,600 feet of stainless steel reinforcement put in this building. And it might seem a little heavy-handed to you, but remember, some of these point loads were 83,000 pounds. Most all of them were in the range of 30 to 35,000 pounds, and that's a huge amount of load. And why that did not set off a red light in somebody's skull when they first calculated that is beyond me. I'm convinced they would have had really serious issues if they would have followed through with the original approach. You've probably seen a piece of stainless steel before, but there you go. You can look at it. Stainless steel reinforcing bars. Here's how the diagonal stitching worked. Just installed at angles in the face of the wall. They were injected in place. The one innovation we had here, we used hollow bars because they also served as injection ports. And so, yeah, it was really nice because we didn't have to drill separate holes for injection. And the guys, like I said, I was really proud of them. I mean, out of I can't remember how many, 800 of these little bars they put in. I can't say they were perfect, but they had to replace 2 or 3 brick on the exterior they went through. You know, their angle was off, or they drilled too deep, but they developed all sorts of templates and jigs and did a really wonderful job of installing all this crazy steel. And we also had as part of the process was developing the injection protocol, and how, you know, if you've got this funny network of holes and rebar and all these things in the wall, how do you make sure you inject this to be solid, all of those spots? And part of that process comes out through the protocol. We actually injected, or had a sequence, injecting first this hole, letting the material flow around and come back to here before they would move on to the next injection ports. And I think we overthought it a little bit. Actually, the material tended to flow 6 to 8 feet from one injection port to the other. It was really a fine mix. So, but they had a protocol that they had to follow to make sure that all of the rebar was filled all the way around there. So the first step in ensuring, if you're involved in an injection process, and I really didn't cover a whole lot of injection of the wall itself, but similar concept, develop the material, develop a protocol, make sure they follow the protocol. The first step in making sure that the wall is injected properly is making sure they follow the protocol. And by that I mean if the material, if they're injecting, goes in one hole, comes out another one 4 feet away, I'm pretty sure it flowed between those points, and pretty sure it filled in that void space in between. The second step to making sure the injection was done right is following through some NDE. And we saw the results of some post-injection, or actually some condition survey radar Here are some other radar traces with different color scheme. I like this one because it's really easy to see, I think. Before injection, scanning down the wall, depth, 15-inch depth here. All of these little reflections mean voids. Lots of voids in the collar joints. And same spot after injection, nearly completely solid. And that's our goal. I don't think the original designer intended there to be voids inside the wall and intended the collar joints to be empty. And our goal then was accomplished in providing a solid wall and the voids inside that wall being filled with a nice compatible material that we'll see in a moment. So that's it. I mean, I had a couple of final thoughts, in thinking about how would we do this differently. Well, I'll tell you, we have some new materials now. We've worked with Masonry Solutions. They actually bought a device that will take these stainless steel tubes, a big cold rolling system, and turn them into deformed bars. And this is one we've been doing a lot of work in New Orleans lately, strengthening pump stations. And this is one of the bars they put in thousands of these bars in pump stations in New Orleans. And they take a stainless steel tube and cold roll it, and that's interesting because you go from about a 30,000 psi yield to 70,000 psi through the cold rolling process. Plus you get the deformations that grab onto the grout better. So we would do that differently now, but I think the main thing I would do differently is we're always working to educate engineers that are really good with new construction, and educate them when they get into old masonry. You got to do things a little differently because the stiffness and strength of these materials are not what they seem to be. I would love to have been involved in this project a whole lot earlier, during the design phase, because it kills me to be involved in a project where the building was essentially gutted and they just replaced the shell with a new program inside the building. But that's how it was in this project.
Mike, you had said that the architect refused to leave sections of the interior wall which
Yep.
would have helped you in your work. Is that because of programmatic reasons or where they already were in the design phase?
I think it was both. They were in construction. I mean, the entire design was done, all the engineering, all the architectural design was done, and it was while they started tearing out floors that the University of Missouri, the architect for the university said, I'm getting a little nervous about this. And so it was because the design was done, and also programmatically they wanted certain spaces in there, and these, I like, what's 6 foot of shear wall? What's 6 foot of bearing wall? It's that much, come on. But that was a no-go. All of that reinforcement, no, not all of it. I'd say 3/4 of it could have been avoided just by giving us just larger bearing areas. Oh well, that's how it goes sometimes. That's why you get the fun projects, right? How do you deal with this? And it's been real successful. I haven't been there recently at the university, about 2 years after it was done, and beautiful. It looks like a wonderful building. Nobody would know that there were very nearly some big issues.
So why were you brought on? What was the background of that conversation?
Wow, you want to know that conversation? It was very collegial because, like I said, we've been working with the University of Missouri on some of their buildings since 94, 95. And, I think it's funny. They tend to call us when they have brick issues and stone issues, mostly on their modern buildings. And their campus architect called me and he's like, hey, we were just talking about it. It's like, yeah, they're doing these things and I don't feel so good about what's happening and it's historic stuff. What? They're putting big beams bearing on these old walls, and we started talking about it, realizing there may be some issues. And we had a good relationship with the engineer. I mean, we really went to great lengths to protect them from the university because, if I was a university, I would have said, you guys did not do your job right because you gave us a design that really won't work. And not only that, I think it was, close the camera, but I think it was unsafe. I think it would have been, they would have had serious problems. So, I think ultimately the university was really happy to get this work done. The engineers were tolerant of it, and the architect, I don't think they cared. They just wanted their space as they designed it. So I guess they were happy that it happened too.
Hey, Mike,
Yes.
when the building was gutted, you said that the floor level shifted. What was the condition of the walls after the floors came out?
So the condition of the walls
Rotted
after oh yeah, there were all sorts of beam pockets in the walls, and they closed those up with brick, and you can see the original brick in some areas, but mostly, one thing I didn't talk about, they furred out the inside of the walls and insulated the interior. And we also got involved, we did some thermal analysis and moisture analysis of the wall system for them and said, don't insulate those walls, they've never frozen for their entire life. And went with the insulation inboard, now the freezing front, Missouri winters are long and cold, the freezing front came in at least 2, maybe 3 wides of brick. And I don't know if you remember, we did the laboratory evaluation of the brick themselves. The common brick was classified as a non-weathering brick. Very low strength, very high porosity, wrong pore structure really for durability. And so I'm convinced they're gonna have some freeze-thaw problems in a few decades. Well, they'll be fine for a while. But that did not meet their energy requirements, and I worry about that. You know, with a lot of what we're doing today, we're concentrating on energy requirements and how that interior insulation affects water vapor transmission through the wall, where the freezing front is within the wall, and more importantly, the condensation front, absolutely changed as a result of interior insulation. And it's been, we've had 3 or 4 projects like that where the recommendation is to the architect is, here's where your condensation front was. It would never would get, maybe it'd get an inch or 2 into the brick historically, but as soon as you insulate it, those walls are always going to be cold, and that condensation front is really, really deep in the wall. That means it's going to be wet, it's going to be damp, it's going to freeze.
You need to do a pre-
So, did you wear your grouting clothes? I did. We'll go out back. I told Drew to be ready at 12:30. It's about a little before 1, so they're no doubt ready by now. This is a core from the New Orleans work. It's mainly a lime mix. You can get into it with your fingernail. You know, it's not a real high strength material. So the lime mixes, we usually wait. I don't know, Zach. How soon do we wait before coring? A week or 2 minimum before we take a core out. Like
about 14 days.
yeah, at least 2 weeks. I mean, the modern grouts. I mean, these are like 5,000-6,000 psi for modern masonry, and that you could core a lot quicker. So you can look at core samples. I actually found one from University of Missouri. And again, what we're looking at is really good contact between the injected material. In this case, it's the whiter material. You see the original mortar was kind of grayish. Really good flow into these little cracks and fissures. Good bond, no shrinkage. A little bit of settlement. You know, that is not our best core, but it happens from time to time. You get a little air void in there. But most of the time, you know, we've got some really good mixes that just bond like mad, but yet they're kind of soft and squishy and have a good vapor transmission. We've been doing lots of vapor transmission tests. We've done mixes, very, very fine mixes for crack injection as well, ultra fine mix. That's maybe somewhat easier to see. You know, just cracks. I think we just finished a project at New York City Hall that we're injecting joints between stair treads, and they were 1/16 of an inch to 3/32 of an inch, and big, long stair treads, and it's pretty easy. I think our maximum penetration is in cracks about 0.07 of an inch and wider, although I've seen it in cracks much smaller. They'll fill it up, stop it, they'll use a stopwatch. What are we shooting for, Drew?
21 to 31.
Yeah, we give them a pretty wide range. We let the contractor adjust the flow depending on if it's a hot, dry day. They may have a little bit higher flow rate. I'm sorry, a quicker flow rate, meaning more fluid. So there's the injection material, and this is the same stuff that you see in these cores. And so it's really fluid. It flows like mad, but over time it will. The cement in there hydrates, the lime in there carbonates, and it gets hard. A little slow.
It's been sitting.
So we have a pressure pot.
Here in New York.
We operate at low pressure, the injection 8 to 10 psi. So it's really different from concrete crack injection, which uses 1,000 psi, 1,500. You get the penetration through good flow, not necessarily high pressure. And we found high pressures can tend to segregate the material. You know, they'll force the water right out of the mix, and things will clog up in the hose, and it's a problem. So usually, the injection process starts with some of the investigative work that you saw. It's our job to figure out how often to put the injection ports. There is some pointing work involved. I mean, this material flows really well. So if there's cracks, generally with a material like this, if we have a crack wider than 1/16 to 1/8 of an inch range, they've got to point it up, or else the material will flow out of there. You guys have already pre-wet the wall, right?
Yes.
We do, after drilling injection holes, and you can see them, they're drilled into the mortar joints. Where's our hole? Oh, here's one.
Here's one. Here's one.
Yeah, we just put them in kind of random here, but typically, I think for like the University of Missouri, they might be 2 feet apart horizontally, 8 to 12 inches vertically. Yeah, we limit the guys to 4-foot lifts in any 4-hour period, and 8-foot max a day. And yeah, that's the process. It looks easy because we built about the simplest type of wall system here with just a collar joint that might be 3/4 of an inch wide. But I tell you, it takes experienced operators to make it work right, because if you're not paying attention, if you're pumping for minutes and minutes and minutes and don't know where it's going, they've had to buy living room carpet, and things that get through voids of the inside face of walls. For bigger projects, they'll use, like the crew will use a pressure pod for a crack injection because it's almost no material. It's like a couple quarts of material goes a long ways in a 1/16 of an inch crack. For bigger projects, they use, like Missouri and all the work in New Orleans, they have silo systems where all the material is pre-blended, shipped down to the site in 3,000-pound bags. A silo feeds into an automatic mixer that automatically doses the water. There's not a bunch of guys with drills and 5-gallon buckets. It's really like industrial scale injection. A lot of they'll go through 3,000 pounds of material in about 2 days sometimes on some projects. A lot of the fixes are structural, like we talked about today, but very often the injection is done to cure water penetration problems, because all the voids that affect us structurally also let water in and let water transmit and travel throughout the wall.